We're going to do part B in this one.
And specifically, like, if that's too much, it was just the very last one. It kept on coming out really easy.
So this one?
Yeah.
Okay. So, yeah, and that'll be enough. If you can get that one, you can get the other one. So find the indicated partial derivatives of the given function. In this case, w is equal to x divided by the quantity 2y plus z. Let's write this down and just kind of refresh our memories as to what it means. So you have the d3w, and then dz, dy, dx in the bottom. So if you write this out using the fact that Leibniz notation looks like algebra, you can figure out what this means even if you're not sure. This means 3 d's, right? D, D, D. And then this first one will be underneath the dz. The second one will be underneath it, I should say, will be dy. Third one underneath it will be the dx. And then there's a w then on this one, if you like. So what are we saying here? We're going to take the first derivative of w with respect to x, and then we're going to take the derivative of that with respect to y, and then we're going to take the derivative of that with respect to z. So w is x divided by 2y plus z. You might want to write it like this: x times 2y plus z to the negative 1, maybe. We'll see if that is going to work out or not. And then what would, on the first one, it doesn't make a difference. If you take the derivative of w with respect to x, what do you get? Well, this is just a constant, isn't it? So then this guy just goes to 1, doesn't it? So if you do that, the partial of w with respect to x then, if I leave it in the negative exponent notation, would be 2y plus z to the negative 1, wouldn't it? Do you buy that so far? But now what are we doing? We're going to take the derivative of that with respect to y, right? So we'll go for partial of the first derivative with respect to x with respect to y, if that makes any sense at all. So the notation would look like that for the second derivative. Oh, well, all right, then you just have to take the derivative of this guy with respect to y. That's not so bad. What do you have to do first? Bring down that. It's the power rule. Bring down the exponent. 2y plus z to the what? Subtract 1. But then you have to remember calculus 1 chain rule. Times the derivative of what's inside those parentheses with respect to y. So just times 2. Everybody believe that? Okay. And then we're going to take the derivative of that with respect to what? Whoops. Probably shouldn't have done that yet. With respect to z. Does that make sense? Okay. So then we're going to do d dz of what we just found. Whoops. That should be x. Okay. Which is the same as d dz. If you wanted to get used to the notation, it would be the same as d dz of this. I could put the 2 out in front as a factor. Negative 2 times 2y plus z to the negative 2, right? Yeah, this last notation is not necessary. I just did it to get you used to it. And then, okay, what's the derivative of that then? Bring down the negative 2. What does that give you out in front? Positive 4 times 2y plus z to the what? To the negative 3. And then do we have to multiply by anything? Well, 1, right? Because now if you take the derivative of the inner function, it's with respect to z, isn't it? So, yeah, you don't have to worry about the chain rule there. And then I would guess in the back of the book, in the answer, I probably wrote it like this, 2y plus z cubed in the bottom.